An aircraft in flight is a marvel of physics, a dance between weight, lift, thrust, drag. A stall can happen at any speed, even at high speed. One of the most persistent myths is the conflation of a stall with engine failure. In everyday language, stall often means an engine quitting, like a stalled car. In aviation, this is incorrect. An aircraft stall is purely aerodynamic and about the wings, not the engine. An airplane can be fully stalled with engines at maximum power. Conversely, it can glide perfectly with the engine off if the wings are not stalled. Separate thrust from lift. Engines provide thrust. Wings provide lift. Another misconception: stalls are only a low-speed problem. We train there often and during takeoff configurations because low speed requires higher angle of attack, close to critical. The truth: angle of attack, not airspeed, directly causes a stall. Speed merely influences AOA. A stall is loss of lift from excessive AOA. An engine failure is loss of thrust. To understand a stall, define angle of attack, AOA. Imagine a straight line through the wing, leading edge to trailing edge, the chord line. Now the direction of air meeting the wing, the relative airflow. AOA is the angle between chord line and relative airflow. AOA is not pitch attitude. You can climb with low AOA or descend with high AOA. Lift relates directly to AOA. Increase AOA and lift increases, up to a point. Visualize a graph. Vertical axis, lift coefficient. Horizontal axis, angle of attack. As AOA increases from 0, CL climbs steadily. The wing turns airflow into upward force. But there is a limit, a precise angle of maximum lift. That is the critical angle of attack. In many light aircraft, around 15 to 18 degrees. Beyond critical AOA, smooth flow can no longer follow the wing. It becomes turbulent and separates. Flow separation. Lift drops, drag increases sharply. That sudden loss is the stall. Before critical, streamlines hug the wing. At and beyond, they peel away into a wake. The wing has not stopped working entirely, but much of its lift is lost. Key takeaway: exceeding a specific angle, not a specific speed, triggers a stall. It can happen at low speed or at high speed. The cause is the same: exceeding the critical angle. The cause is always the same: exceeding critical AOA, but contexts vary. Classic low-speed stall: approach to landing or just after takeoff. Low speed demands higher AOA to maintain lift. Too steep or too slow, and AOA exceeds critical. Stall. Accelerated stall, turn-induced, proves stalls are not just low-speed events. In a turn, wings must counterweight and provide extra force. Increased load factor. At 60 degrees of bank, lift demand doubles. Generate extra lift by increasing AOA. Pull too hard, and the wing stalls well above the straight and level stall speed. High-speed stall. A rapid pitch-up steepens the relative airflow, spiking AOA past critical. Even with plenty of speed, separated flow means stall. These names describe conditions, not causes. In every case, one reason: AOA became too large, and airflow separated from the wing. Modern aircraft have layered safety to help avoid unintentional stalls. Long before a full stall, warnings appear. Aerodynamic buffet is common. As AOA nears critical, turbulence flows aft and creates a noticeable vibration. Buffet. Pilots sense it through the controls. Artificial warnings add clarity. Horn, buzzer, synthesized voice, typically at a preset margin before stall. Many aircraft include a stick shaker to simulate deep buffet. These are designed to be unmistakable. Recovery is core training, practiced to instinct. Steps are simple, logical, universal. Reduce the angle of attack, push the nose down. That restores attached flow and lift. Add power to minimize altitude loss. Level the wings and stabilize. Then gently raise the nose back to normal flight. Stall awareness and recovery are embedded in training and certification. From the first lessons, pilots learn stalls in controlled environments. They feel the controls, hear the warning, sense the buffet. Repetition builds muscle memory and calm responses. Aircraft must show safe, predictable stall behavior for certification. Test pilots explore stalls across weights, centers of gravity, and configurations. Warning systems trigger well before published stall speeds. Design, warnings, and training form a layered defense. The wing does not know speed or engine status, only angle of attack. Manage that one critical angle, and the wing keeps flying. A stall is not about speed, it is about angle. Subscribe for more aviation theory explained clearly.